Now, in this session, let us discuss about voltage regulation of transformer, distribution transformer, power transformer, alternator, everything has to be discussed. Actually, as textbooks give, it is not about the formula. It's not about equations. We have to understood properly. We have to analyze properly why, like, kind of significance of voltage regulation. Maybe it will open the doors to alternators also. In alternators also, basically, if we understand voltage regulation properly, okay, under that conditions, like in synchronous machines, in alternators, they will give small problems without even touching the calculator also. We will be able to solve some problems. So voltage regulation discussion should be very extensive. Means in voltage regulation we are going to discuss about distribution transformer. Okay, distribution transformer means that whatever with the transformer which is giving power supply to household, okay, to your homes, like distribution, from a distribution transformer secondary only we are going to get the power to our household. Okay, and after that power transformer will be there, means small capacity power transformer. These distribution transformers will be connected to power transformer. So means distribution transformer primaries will be connected to power transformer secondary, and again high capacity power transformers. Okay, means that low capacity power transformers will not have reactive power injection. In the sense, there will not be any capacitor banks and all. And high capacity power transformers, reactive power injection will be there. In the sense, capacitor banks will be there. Depending upon the need of reactive power, they may connect the capacitor banks to the power transformer. Now next thing is we have to think about alternator also. In alternator, reactive power is inbuilt. Okay, in this case, at the end of this discussion, you have to get the conclusion that maybe for these two only, maximum voltage regulation and zero voltage regulation we have to analyze. And for alternator and when power transformer connected with reactive power injection, we should not focus on calculating maximum voltage regulation or zero voltage regulation, should also be understood. Okay, now basically if I think of distribution transformer, okay, this is distribution transformer. So if you think of distribution transformer output will be connected to your household. Okay, so in three phase it is going to be around 11 kV. In three phase, line to line, it's going to be around 440 volts. Okay, roughly 440 volts. Now, of course, it is going to be three phase. Now, if you convert into single phase, roughly 230 plus volts will be there. Now, means the moment it is connected to our household applications. Why voltage regulation of a distribution transformer is important if we see. Basically, in our household, we have means lighting loads. In the sense, incandescent lamps can be there. Kind of fluorescent lamps can be there, kind of induction motors will be there. Our household loads are dominated by these three. Okay, now let us think of what they say incandescent lamp. If you think of incandescent lamp, in incandescent lamp I am going to have tungsten filament. Okay, so I am going to have tungsten filament. Okay, so this tungsten filament is going to absorb some electrical power that will be converted into heat energy. That heat energy will make the tungsten filament from normal to red hot condition to white hot condition. Now, means the light energy emanated by this incandescent lamp will be decided by means heat energy. That heat energy will be decided by electrical power input. Now, means if I supply some voltage here, this is going to be pure resistance only. Okay, that is going to be tungsten filament resistance only. So, if I think of electrical power absorbed by this is going to be V square by resistance. Okay, for example, if voltage because of some reasons, if voltage across this vary, under that conditions electrical power absorbed by incandescent lamp will vary. If electrical power absorbed varies, automatically heat energy will vary, automatically light energy emanated from the incandescent lamp is going to vary. Now, next thing is fluorescent lamp. Fluorescent lamp, if you supply less than around 180 volts, it will not start the initiation of glowing itself. Okay, fluorescent lamp. Now let us think of induction motor. Okay, because fluorescent lamps and all will come in utilization. Anyway, let us think of our induction motor. In induction motor, maybe because of voltage variation of distribution transformer, for example, this is reduced. Means that voltage supplied to induction motor is going to reduce. Under that condition, V by F ratio is going to reduce. Okay, for a given frequency, if V by F ratio reduces, automatically flux is going to reduce. Okay, means already we know that in transformer V by F ratio directly proportional operating flux we have seen. Now if flux reduces, already we know that torque is directly proportional to pi I. So my flux is going to reduce. If flux is going to reduce, what will happen to the torque? Can I say torque reduce? No. Why? Because torque requirement will be decided by the load. Okay, so for a given torque requirement, for example, my ceiling fan is there. Okay, so the moment it's a fan load, torque requirement is going to be directly proportional to speed square. So torque requirement will be decided by the load. Now if your electrical motor is able to meet that particular demand of torque, it will rotate. If it is unable to, it will stop. That's it. Okay, so torque requirement will be decided by the load. For example, I repeat, for example, if torque requirement is constant, I repeat, for example, torque requirement of the load is constant. Under that condition, flux reduced. So in order to meet the same load requirement, my current has to be increased. Now, if this particular voltage is reduced much, under that condition, V by F ratio is going to reduce much, operating flux is going to reduce much, and in order to meet the same load torque, my current increment can be more than designed value. Okay, so for example, in my induction motor, if the copper wire in primary is designed for 10 amperes, if it is more than 10 amperes, my induction motor is going to burn. Okay, so we can conclude that all utilities connected, performance means is influenced by voltage profile maintained. So voltage profile we should know. Okay, that's why means we need to calculate voltage regulation for a distribution transformer. Means let me repeat again. Voltage regulation for a distribution transformer is going to be very significant, because depending upon voltage profile maintained across distribution transformer only, all performance of all utilities will be decided. Okay, so in order to have better utility performance, I should be able to maintain better voltage profile. Now I should know the voltage profile variation here. That's why I should know voltage regulation of transformer. Voltage regulation in the sense from no load to load, how much voltage is going to be varied, or voltage profile will come to know through voltage regulation only. Now let us think of power transformer. Okay, so in power transformer, if you see, in power transformer, voltage regulation, why it is important? Okay, so if you think of, for example, power transformer, okay, maybe very big power transformer, let me consider. So this is 110 kV. Okay, everything I'm using in three-phase equivalent. Okay, now input is 110 kV, output is 220 kV. Okay, now in power transformer you are going to have tap changer or not? Yes. Okay, so means for example at no load condition it is going to be 220 kV, 110 kV by 220 kV power transformer. Okay, basically this tap changer will not be there, or at least on load tap changer will not be there in distribution transformer, because means for example if you think of distribution transformer, it will be thrown adjacent to the roads. Okay, so at each and every distribution transformer, can you ask your operating engineer to sit and to vary the taps? No. So means for my distribution transformer, tap changer, on load tap changer, okay, some kind of hard coated tap changer will be there. I will discuss about that later. But anyway, on load tap changer will not be there, because we cannot keep operating engineer here. And now maybe some guys can think of, okay, means automatic on-load tap changer. If we keep, what will happen? Okay, basically automatic on-load tap changer we are not using. Okay, we are using manual on-load tap changer only. On-load tap changer in the sense, while load is connected, means under that load connected conditions only we are going to change the taps. That is on-load tap changer. Off-load tap changer means that we have to disconnect the load and then change the taps and then connect the load is going to be off-load tap changer. Okay, so on-load tap changer we cannot place because automatic on-load tap changer we are not using. Okay, the greatest irony is, means in order to have automatic on-load tap changer, it is very costly compared to operating engineer salary. Okay, so means we use manual on-load tap changer only. In India we are not using automatic on-load tap changer because you can think of, if automatic on-load tap changer is being used, maybe in distribution transformer also let us keep inside one tap changer, we are not using that. Okay, inside some off-load tap changer or hard-coded tap changer will be there. About that I will discuss later. Okay, coming to the point here. Okay, means at no load condition, for example, tap is here. At no load condition I am getting 220 kV. Okay, at the secondary. For example, let me connect load. Okay, for example, let me connect load. Okay, so because of load current, for example, my terminal voltage is supposed to be reduced maybe to 170 kV. Of course, that much variation will not be there, just for explanation I am taking. Okay, so means it is 220 kV at no load condition. The moment load is connected, my terminal voltage is drooping to 170 kV. Under that conditions, what will you do as an operating engineer? If you are an operating engineer, you will increase the taps such that you are going to change the tap from here to here. Okay, you are going to change the tap from here to here such that means this 170 will be boosted back to 220. So independent of loading conditions, okay, can I maintain 220 kV constant in power transformer or not? Yes. Okay, because the moment it's a power transformer, it's going to handle bulk of power. So our separate substation will be there and our separate operating engineer will be there. That operating engineer can manage this manually. Okay, so because of loaded conditions also I can maintain same terminal voltage in case of power transformer. So this is power transformer, PT, power transformer. Okay, so logic here is why we need to calculate voltage regulation for a power transformer. Okay, because for a distribution transformer, why we are calculating voltage regulation is because my distribution transformer secondary is directly connected to the utilities. Okay, and all those utilities performances are influenced by voltage profile maintained by the distribution transformer. So means at what particular load how much is the voltage is being maintained across the distribution transformer, we should know. Okay, now if you think of power transformer, why we need to calculate voltage regulation? Because whatever may be the load it is, the moment you have control over the taps, we can maintain the same voltage. Now my question is, why we need to calculate voltage regulation for a power transformer? Okay, if you think of, for example, how much should be the capacity of tap changer? Okay, how much should be the capacity of tap changer? Should be decided by, for example, at no load conditions it is giving 220 kV. At full load conditions, at given power factor, this particular voltage is supposed to be reduced to 170. Now, means this particular tap changer should be able to complement how much kV? 170, 220, in the sense 50 kV. So this particular tap changer capacity should be to complement 50 kV. So this particular tap changer capacity will be decided by this particular boost up. R is nothing but drop here. This drop is nothing but voltage regulation only. Okay, so means for my power transformer, first point is, in order to design or in order to decide the capacity of tap changer, voltage regulation should be known. Capacity of tap changer. Okay, now next thing is for example, if everything is going smooth at full load current conditions. Now for example, if fault occurred, okay, so for example, if fault occurred here, if fault occurred here, this particular circuit breaker, okay, this is going to be circuit breaker immediately will isolate the faulty section or not. Okay, so means under normal healthy conditions there will be no problem, but when fault occurs, this circuit breaker simply isolate the faulty section as soon as possible, and in that condition means how much will be the voltage shoot up. If you observe, for example, see here black, okay, so now see here, okay, so starting at no load condition, this is going to be the tap. At no load condition, how much is the voltage? 220 kV. Now at loaded condition, the 220 kV has been reduced to 170 kV. Now I increase the tap such that my voltage is increased to 220 kV again. Now where is the tap? Tap is here. Now tap is here. Now fault occurred. So immediately what my circuit breaker has done, it has isolated the faulty section. Means that the moment it is isolated the faulty section, how much is the load current is going to become 0. So my transformer all of a sudden will come down to no load. Now at no load, if I keep the tap here, it is 220 kV. But if I keep the tap here, it will be more than 220 kV. So my voltage will be shooted. To 270 plus 50. 220 plus 50 is going to be 270 kV. Okay, so in order to know the rise in temperature, because depending upon this rise in temperature, insulation may have to be designed. Okay, so point is very simple. What is that? Means under faulty conditions, or when load is suddenly thrown off. Okay, when load is suddenly thrown off due to fault, under that condition my voltage will be shooted. Let me repeat again. Relax. See here, at no load conditions it is here. Okay, so at no load conditions it is here, my tap is here. Now at loaded conditions, what has happened? My voltage has been reduced from 220 kV to 170. So I increase the tap from here to here such that this 170 is improved to 220 kV. Now means all of a sudden my section or load is completely disconnected. Under that conditions, what will happen? If I keep the tap here, it is going to be 220 at no load. But if I keep the tap here at no load, why it became no load? Because of faulty section. Okay, so because of faulty section, the moment load is withdrawn completely, all of a sudden under that conditions voltage will be shooted up. Okay, now how much is going to be the voltage shooted up? Depending upon that, my insulation may have to be designed at least at bushings and all. Okay, so point here is we should know rise in temperature rise in order to design insulation. Okay, now let us think of alternator. Okay, I know that we did not discuss alternator, operating principle, what is happening inside. That's a different story, we will see later. Now means, but at least let me think of alternator. Okay, now let me think of alternator. Okay, so for example, this is alternator. Okay, for this alternator, output voltage is 11 kV. Output voltage is 11 kV with a field current. Okay, with a field current of some IF. Okay, so means in alternator we are going to rotate. For example, my conductors are being rotated. So for example, these are going to be conductors. In the rotor. Now conductors are being rotated, and this is going to be pole, N pole, S pole. Inside N pole, S pole, my conductors are getting rotated. Now because of this rotation, N d pi by dt will be there. Because of that, induced voltages will be there here. Now that induced voltage is 11 kV for a given rotation, given speed and field current. Now for example, if load is connected. Okay, so for example, if load is connected, load current is connected. Okay, under that condition, for example, of course, in alternator not only leakage will be there, but also armature reaction also will be there. We will see in alternator. But anyway, this 11 kV is reduced to, for example, 5 kV. 5 kV. Under that conditions, what will you do? What will you do? You are going to increase the field current. You are going to increase the field current such that for a given speed, direction of rotation and speed of rotation is going to be same. Now this is N pole. If this N pole is producing more flux lines for given speed only, N d by dt is going to be more because flux is more. Okay, so because of that means the moment field current is increased, my voltage will be coming back to 11 kV. Now, at no load also, my output voltage, terminal voltage in alternator is 11 kV. At loaded conditions also, by varying field excitation, okay, by varying field excitation, I can maintain the terminal voltage constant at 11 kV independent of loading conditions. Okay, under that condition, at no load also 11 kV, at full load also, for example, 11 kV. At 0.8 pf lag also 11 kV, at 0.8 pf lead also 11 kV can be maintained by varying field current. Under that condition, why should I calculate voltage regulation of an alternator? Again, same old story. For example, means here if fault occurs. Okay, under that condition, for example, at no load, one flux line is there. For example, at no load, one flux line is there and it is rotating with some speed. These are my conductors. At no load, one flux line is there. I am getting 11 kV here. Now it is loaded means that my load is connected. So because of my connection of load, terminal voltage is reduced because of some nonsense reasons. Okay, so terminal voltage is reduced to 5 kV. Under that condition, what I am going to do? I am going to increase field current. Such that flux lines will be more. So for the same speed, induced voltage will be more. Such that this 5 kV will be shooted back to 11 kV. Now fault occurred. Immediately what my circuit breaker will do? Circuit breaker will isolate the faulty section. The moment it isolates the faulty section, what is the load current here? 0. So suddenly it will come down from loaded conditions to no load. Okay, loaded condition, no load. Now at no load condition, for example, at no load condition, if I have one flux line, it will be 11 kV. At loaded condition, I increased flux lines to 4 flux lines such that it will be maintained at 11 kV. Okay, and loaded condition. Now all of a sudden circuit breaker got isolated. Isolated the faulty section. So this became no load. Okay, my alternator became no load because my circuit breaker isolated the faulty section. Under that condition, already increased field current will be there. Increased 4 flux lines, field current will be there. So increased field current will be there and speed of rotation is going to be same. My induced voltage here or this particular 11 kV will be shooted. Okay, now why voltage regulation is important or significant for power transformer or what do you say alternator? Because of two things. First thing is in transformer to decide the capacity of tap changer and to decide the insulation design. Now if you come to here, for example, at no load conditions, my alternator output voltage is 11 kV. At loaded conditions, it is 5 kV. What is the difference? 6 kV. So 6 kV should be shooted up. Means that in order to shoot up 6 kV or in order to complement 6 kV, how much field current should be used? How much field current should be excited? More field current. Okay, so how much more field current has to be injected? Depending upon that, my area of cross section of the copper of the field winding has to be designed. Okay, so my area of cross section of the field winding will be deciding factor for the maximum field current. That maximum field current will be decided at the dip in voltage, means that complemented voltage. So design of this will be decided by this. Voltage regulation, voltage variation. Now means, for example, field current is increased to here, such that my 11 kV is maintained here at loaded conditions. Now if fault occurs and if circuit breaker isolate the faulty section, this is going to be shooted because already increased the field current is there. So because of that, induced voltage will be shooted. That shooted voltage is required in order to design the insulation of alternator. So voltage regulation is important for power transformer or alternator, because for power transformer capacity of tap changer will be decided by voltage regulation, and in case of alternator my excitation system or field current, okay, or field circuit design will be decided by voltage regulation. And second thing is see here, insulation level, okay, should be designed by voltage regulation. Here insulation level should be designed by voltage regulation. Now let us think of, okay, what is the definition of voltage regulation? Okay, because we have seen already distribution transformer, power transformer and also alternator. Okay, basically power transformer and alternator is almost kind of equation wise they are same. Why, you will come to know slowly. Now let us think of distribution transformer. In distribution transformer, first of all, means let me ask you one question. This voltage regulation, you know that no load voltage to voltage load or full load or whatever it may be voltage with respect to rated voltage is nothing but voltage regulation. Okay, detailed definition I will give you, just wait. Okay, now means this particular voltage regulation, no load voltage to full load voltage or any load voltage. Okay, no load voltage variation from no load to full load or any load, it should be any load for distribution transformer, it should be full load for the power transformer or alternator. Because if you think of, for example, outside your house, okay, if you stay in apartment, each and every apartment mostly is having one distribution transformer. Okay, so if you have one distribution transformer, that distribution transformer output will be directly connected to our homes. Okay, now if you want to switch on your television or TV, you are going to switch on, otherwise you are going to switch off. If you want to switch on your AC, then only you are going to switch on, otherwise you are going to switch off. Okay, so for example, when your AC at your home is connected and is switched on, then only that particular load will be there on the distribution transformer, otherwise there will be no load on the distribution transformer because of your AC. Okay, so means my distribution transformer load will be decided by customers, Okay, so my distribution transformer means loading conditions of the distribution transformer will be decided by the customers. Now, for example, okay, let me take one simple example. Okay, for example, with me, right side one street is there, rasta, one street is there, left side one street is there. Okay, right side street, all the homes are belonging to engineers only. Okay, they will go to morning to office and evening they will come back from office. So these guys, okay, and these guys, for example, in the street, all the guys are from BPO. Okay, so telephonic support. Under that conditions, for example, all these guys are going to office at evening and they will come back in the next day morning, for example. Okay, so for example, maximum demand for engineers transformer is 5 kVA and maximum demand for this BPO guys, of that particular transformer is also 5 kVA. Okay, now for example, if you think of this transformer which is connected with engineers, morning they will go to office, till evening they don't come. So morning to evening there may not be any load on this particular distribution transformer. And in the evening, once our engineers come back, under that condition they will try to utilize the electrical power. So this particular transformer will be loaded in the night time only. Okay, now if you think of this particular distribution transformer, night times they are going to office, so daytimes they don't go to office. So daytimes load will be there on this particular distribution transformer, night times there may not be any load. Now, for example, these two distribution transformer are connected to power transformer. For example, power transformer is me. Okay, so power transformer will be almost loaded at full load conditions. For example, this is distribution transformer 5 kVA which will be loaded during night time. This is distribution transformer of again 5 kVA which will be loaded on daytime. Now, what should be the capacity of power transformer to me? Power transformer of mine should be the capacity of 5 kVA only. Okay, that is diversification factor. Okay, in the sense catchment area, let us think of what is diversification factor, the exact definition, some kind of stuff we will see in the power systems. Okay, so means point is very simple. Okay, so for example, if power transformer capacity is 5 kVA, during daytime it will give it to, what they say, these particular BPO guys. During night time it will give it to engineers. Okay, so engineers, distribution transformer load variations will be high. It can operate at completely no load, it can operate at completely full load, it can operate at half full load. BPO guys, distribution transformer may operate at full load, okay, or cannot operate at half full load depending upon the loading condition of the distribution transformer supplied to BPO guys, this particular street. Okay, so if you keenly observe, this distribution transformer can operate at any load including no load condition. For example, if these two distribution transformers are connected to a power transformer, this power transformer will supply power during daytime to them and during night time to them, such that load variation on power transformer is going to be less or none. Yes, because catchment area is two streets for it. Okay, so one thing I have to tell you here, distribution transformer, I repeat, this is very important, distribution transformer can work on any load, any power factor. So while defining voltage regulation of a distribution transformer, no load to any load at any power factor should be set. Now if you think of these two transformers are connected to power transformer load variations are going to be less. Why? Diversification factor is more. For example, a big power transformer, if you see, for example, if these guys don't require any power, it will give it to these guys. If these guys don't want any power, maybe it will supply to somebody else. So diversification factor is more for a power transformer. So that's why load variations are going to be very less for a power transformer. Okay, now the moment load variations are going to be very less, I can say that power transformer always almost operate at full load. Okay, so distribution transformer load variations will be more because diversification factor is less. Power transformer always almost operated full load. Okay, always almost operated full load because of high diversification factor. Now if you think of alternator, once alternator is connected with infinite bus, national grid. Okay, so once it is connected with national grid, for example, if complete Telangana is not in need of power, it will supply to Andhra Pradesh. If complete Andhra Pradesh is not in need of power, maybe it will sell it to Uttar Pradesh. Okay, so point here is, once my alternator is connected with national grid, complete India is going to be, what do you say, catchment area for the alternator. So alternator always operated full load. So how to define voltage regulation? For a distribution transformer, voltage variation should be considered from no load to any load. Power transformer, no load to full load. Alternator, no load to full load. So conclusion is very simple here. Okay, so conclusion is going to be okay, so conclusion, if you think of distribution transformer, load variations are more. Okay, why load variations are more? Yes, diversification factor is going to be less. Catchment area is going to be less. What is diversification factor? That particular, what do you say, definition and all we will see in power systems. Now next is going to be power transformer. Load variations are going to be very less. Our power transformer almost always operated full load. Almost always operate at full load. Why? Diversification factor is high. Okay, so diversification factor is high. Okay, now if you think of alternator, once it is connected with national grid. Okay, so alternator, once it is grid connected, under that conditions, always operated full load. Why? Diversification factor is going to be highest. Our catchment area will become all over India. Now let us define voltage regulation for a distribution transformer. Okay, for a distribution transformer, voltage will be drooped. Okay, from no load to any load, voltage variation will be dropped. So, means voltage regulation for a distribution transformer is defined as magnitude, I repeat, magnitude of terminal voltage variation from no load to any load at a given power factor expressed as percentage of rated voltage should be voltage regulation for a distribution transformer. Okay, let me repeat again. Magnitude of terminal voltage variation from no load to any load at any given power factor expressed as percentage of rated voltage is nothing but distribution transformer voltage regulation. Now let us define voltage regulation for power transformer or alternator. Okay, for power transformer or alternator means if suddenly load is thrown off. Okay, when suddenly load is thrown off, under that condition my voltage will be shooted up. Okay, so means my voltage regulation for power transformer or alternator should be what is it defined as magnitude of voltage, means magnitude of rise in terminal voltage from no load. Okay, I'm sorry, let me repeat again. Okay, means voltage regulation for power transformer or alternator should be defined as magnitude of rise in terminal voltage from full load. Why? Because almost always I operated full load power transformer. So from full load at given power factor to no load. Okay, from full load at given power factor to no load, when that particular case can happen because of the failure. Okay, so because of the fault, if load is suddenly thrown off from full load to no load, it has to come. Under that condition, shoot up of voltage will happen. So means my voltage regulation for power transformer or alternator should be defined as magnitude of rise in terminal voltage from full load at given power factor to no load expressed as percentage of rated voltage. Now we have to think of what is meant by rated voltage now. Okay, then we can start writing some kind of equations. Okay, so let us think of what is rated voltage. Okay, till now many guys might have this question in their mind. For example, if I say 10 kVA 250 volts by 2500 volts transformer means are there no load voltages or full load voltages? Basically means if I think of this as distribution transformer, the moment it's a distribution transformer, tap changer will not be there. Okay, tap changer will not be there. If tap changer is not there, for example, if you think of drawing a equivalent circuit, approximate equivalent circuit, this can be RE2, XE2. Okay, so this is going to be RE2, this is going to be XE2, and this is going to be Z0 shunt branch. Okay, and this is going to be V1. Okay, and this is going to be I2. Okay, now because of this shunt branch, are you getting any terminal voltage variations? No, because V1 by Z0 current will flow through this, that's it. Now this particular current will not give any voltage variation across the terminals, so shunt branch need not be considered in the analysis of voltage regulation. Only series branch has to be considered. For example, if it is E2, at no load conditions, how much is the voltage here? E2 only. Now means at no load condition, how much is the voltage? E2. At loaded conditions, E2 minus drop is going to be V2. Okay, now means for example, if I say 250 volts by 2500 volts, what does it mean? I don't have any tap changer. Means that if I supply 250 volts at no load condition, voltage is going to be 2500 volts. Okay, because the moment it is loaded, depending upon the magnitude of current, if magnitude of current is more, voltage drop is going to be more. Under that condition, E2 minus drop, voltage variations is going to be high. Okay, now for example, if I2 equal to 0, under that conditions, voltage drop is going to be 0. E2 is nothing but V2. Okay, so this particular 250 by 2500 volts, they should have given in the nameplate detail. If nameplate detail suggests that 10 kVA by 10 kVA 250 volts by 2500 volts means that this particular 250 volts should be no load condition voltage, 2500 volts also should be no load condition voltage only, because under loaded condition, depending upon the loading conditions I2 and theta 2, depending upon loading conditions I2 and theta 2, terminal voltage will vary. That variation, how they can keep as constant in the nameplate detail? Not possible. So basically they are no load voltages. They are no load voltages. So whatever is given on the nameplate detail will become a rated voltage. I repeat, whatever is given in the nameplate detail will become a rated voltage for that machine. Okay, so if you think of distribution transformer, okay, in distribution transformer, nameplate details always should suggest no load voltages only. So no load voltages are going to be rated voltages in distribution transformer. For example, let us think of the same details as power transformer, then we will be able to understand. Okay, for example, I am giving the same. Okay, so this is also 250 volts by 2500 volts. If I say this as power transformer, what does it mean? Power transformer. For example, if I think of the moment it's a power transformer, means tap changer will be there. So let me draw tap changer. Okay, so this is going to be tap, 2500 volts. Now for example, if load is connected, under that condition, this particular voltage is supposed to be dropped, but I don't allow that, but I will increase the tap, I will change the tap such that this voltage will be maintained. Now one thing, what is that? If this current is half full load condition, then also by varying the taps, same 2500 volts can be maintained here. If my load current is even at full load conditions also, by varying the taps I can maintain 2500 volts. Okay, so again nameplate detail will give you the rated voltage, but means whatever may be the nameplate voltages can be maintained across the terminals independent of loading condition I2 and theta 2. Okay, so independent of loading conditions means that even when you operate your power transformer at full load conditions also, even you operate your power transformer at full load conditions also, terminal voltage can be maintained at rated by varying turns ratio. So the moment it's a power transformer, means this particular 2500 volts, if you maintain 250 volts in primary LV side, means secondary voltage is going to be 2500 volts independent of loading condition. And power transformer should always almost operate at full load, so always operate at full load. Okay, so what does it mean? This is going to be full load voltages. Okay, so in power transformer, rated voltage is going to be full load voltage, because power transformer basically we need not say full load, or at half full load also same voltage can be maintained or not. Yes, at 1/4 full load also same voltage can be maintained or not. Yes, but if you think of power transformer always almost operate at full load, means what does it mean? Even at full load conditions also I can maintain 2500 volts across terminals by varying turns ratios. So rated voltages are going to be full load voltages in power transformer. For example, let us think of alternator. Alternator, if I say 11 kV is alternator voltage, that 11 kV, is it no load voltage or half full load voltage or 3/4 full load voltage or 1/4 full load voltage or full load voltage? Anything. Okay, because field current, excitation current is in your hand to control. At no load also 11 kV can be maintained, at 1/4 full load also 11 kV can be maintained, at half full load 0.8 BF lag also, what do you say, 11 kV can be maintained, at half full load 0.8 lead also 11 kV can be maintained, even at full load conditions also 11 kV can be maintained across terminals. Okay, so for alternator, if I write 11 kV, what is that voltage? That is going to be rated voltage. That rated voltage can be maintained independent of loading conditions by varying the field current in alternator. Okay, so basically alternator once it is connected to national grid, Okay, once alternator is connected to infinite bus or grid connected, under that conditions complete India will become catchment area for that alternator. Okay, under that conditions alternator will operate at full load only. Okay, so the moment it is operating at full load, it means even when alternator is operating at full load conditions also 11 kV can be maintained, which is rated voltage. So rated voltage is going to be full load voltage for alternator. So see here, if I think of rated voltage equal to full load voltage in power transformer and alternator. If you think of here, rated voltage equal to no load voltage. Okay, so because of lack of this tap changer, for example, tap changer is not there. Okay, if you supply for example 250 volts, 2500 volts will come only at no load, because at only no load voltage drop will not be there. 2500 will come. At loaded conditions, voltage drop, for example, if it is at half full load into ZE2 voltage drop, E2 minus drop is going to be V2. V2 is going to vary. It will not be 2500. Okay, so the moment any transformer is a distribution transformer, at no load conditions only rated voltages can be maintained or nameplate voltages can be maintained. The moment it is loaded, under that condition my terminal voltage vary. So what is the standard here? This should be rated voltage. That rated voltage is there at no load conditions only. So rated voltage is going to be no load voltage. Now let us try to write the equations now for the voltage regulation. Okay, now let me repeat voltage regulation for distribution transformer. For distribution transformer, what is the definition? Means voltage regulation for a distribution transformer can be defined as magnitude of drop in terminal voltage from no load to not full load, because distribution transformer can operate at any load. Okay, again let me repeat, the voltage regulation of a distribution transformer can be defined as magnitude of drop in terminal voltage from no load to any load with any given power factor expressed as percentage of rated voltage. So no load voltage magnitude minus any load voltage, because it is distribution transformer at any given power factor, divided by rated voltage. Okay, is going to be, what is no load voltage? E2 minus what is load voltage? V2. Okay, E2 is inside and V2 is outside, divided by what is rated voltage for distribution transformer is no load voltage only, is going to be E2 into 100% percentage of rated voltage. Now let us think of voltage regulation of power transformer and also alternator. Okay, in alternator also similar equation will come about the nomenclature change, terminology change we will see in alternator. Anyway, power transformer. Okay, voltage regulation of power transformer can be defined as magnitude of rise in terminal voltage from full load, because power transformer almost operated full load. Now let me start again. Voltage regulation of a power transformer is defined as magnitude of rise in terminal voltage from full load at a given power factor to no load expressed as percentage of rated voltage. What is rated voltage for power transformer? Full load voltage. Now see here, no load to full load drop or full load to no load rise is same. Okay, so no load 220 kV, for example full load 170 kV, or full load 220 kV, no load rise is 270 kV, anything is same. So it is going to be no load minus full load at any given power factor divided by full load. Okay, so no load voltage minus full load voltage by full load voltage into 100% is voltage regulation. Now some of the textbooks say that E2 minus V2 by E2 into 100% is voltage regulation down, and E2 minus V2 by V2 into 100% is voltage regulation up. Okay, it will not be like that. Okay, of course, some book, I don't want to name that book. Voltage regulation up, voltage regulation down will not be there here. Voltage regulation, the purpose of voltage regulation is to know the voltage variations. Okay, and in power transformer and alternator, this particular voltage is going to be rated because that rated voltage can be maintained independent of loading conditions. Independent of loading conditions by varying turns ratio in PT and by varying excitation in case of alternator. So full load voltage is going to be the rated voltage, nameplate detail voltage. Now if you think of no load, so E2 minus V2 by E2, already we know, this is going to be no load voltage is E2 minus full load voltage is V2 at full load divided by V2 at full load into 100%. Now here a small friction will be there between these two, which formula to use in the exam, how to identify whether it is power transformer or distribution transformer. Okay, all these things I will handle. All these things I will handle because some problems I will take and I will force you to think whether given problem is distribution transformer or power transformer. Okay, immediately in the next session we are going to deal with the how to derive equations and what are the significance of maximum voltage regulation, zero voltage regulation. And maximum voltage regulation, zero voltage regulation are very important for distribution transformer and power transformer without having any reactive power injection. And this particular maximum voltage regulation and zero voltage regulation are not at all significant. Nobody should ask any question, ideally speaking, in maximum voltage regulation and zero voltage regulation for a power transformer with reactive power injection or alternator. We will see in the next session. Thank you.